To combat red light running crashes, many states are adopting photo red enforcement programs. In these programs, red light cameras installed at dangerous intersections photograph the license plates of vehicles that run the red light. How effective is this? The Virginia Department of Transportation conducted a comprehensive study in June 2007. The data, measured as the number of crashes caused by red light running per intersection per year for 13 intersections in Fairfax County, is in the table. Analyze this data. Run a hypothesis test to determine if installing the camera helps. To do that, I realize that the data is matched by the intersection, and I'm going to run the test based on taking the differences between these matched values, and I have to decide how I'm going to subtract. So I'm going to take the data before the camera and subtract the corresponding data after the camera was installed. The average of this difference data is 1.007, and the standard deviation, both of which I obtained from my calculator, is 1.209. I'm going to define mu sub d as the mean of the difference in values for the population of intersections. And then to run a test, I'm going to set up a null and alternative hypothesis. And I'm charged here to try and prove or show that there's statistical support for the camera being helpful. I notice the way I subtract is before, subtract, after. The camera is helpful if it reduces the number of accidents. So the camera being helpful would make the after data less than the before, and so the difference, the average of those differences, would be greater than 0. That's what I want to prove, that the camera helps, that the number of accidents after the camera was installed is less. So before, subtract, after would have a tendency to be greater than 0. The null hypothesis is what I'm assuming, and I will assume that it doesn't help, that mu sub d is less than or equal to 0. So that would be step 1. Step 2 would be my sampling distribution. I'm testing against 0. My standard error would be the 1.209 standard deviation, and that's from the sample of the differences. My sample size is 13, so I get 0.3353 is my standard error. This is an upper tail test. Alpha is equal to 0.05. My degrees of freedom is n subtract 1, so 13 subtract 1 is 12. And if I go to the table, I get a critical value of 1.782. My rejection rule is to reject h sub 0 if my test statistic t is greater than 1.782. And step 4, to calculate that test statistic, I will take my sample average, d bar, subtract what I'm testing against, divided by the 0.3353, and get a value of 3.003. Conclusion is to reject h sub 0 since my test statistic value is greater than my critical value, and I conclude that there is statistical support for the camera being effective. The camera helps. You can also calculate a p-value. My test statistic is 3.003, and if I go to the t-table in the book under row 12 for 12 degrees of freedom, I see that the 3.003 is right between 2.681 and 3.055, the last two columns. So the range for my p-value has to be somewhere between 0.005 and 0.01. If I use Excel to calculate an exact p-value, I get 0.0055. And since that's less than 0.05, my risk is even smaller than my 0.05 risk that I was willing to take in making a type 1 error. I reject h sub 0 and have good confidence that I'm correct in doing that I have not made a type 1 error.